Assalamu alaikum and a very good day to all. So I'm recording our class for today. Okay, let us continue with the example of the application for drying. Yeah, and I think we have stopped last class with this example 7.4 from the textbook. Yeah, efficiency of a potato dryer. How we can calculate the efficiency of a dryer, and in this example, the drying of food, which is potato. Okay, a dryer reduces the moisture content of 100 kilogram of potato product from 80% to 10% moisture. 250 kilogram of steam at 70 kilopascal gauge is used to heat the amount of air of 49,800 meter cubic of air to 80 degrees Celsius, and the air is cooled to 71 degrees Celsius in passing through the dryer. You are required to calculate the efficiency of the dryer. The specific heat of potato is given as 3.4 kilojoule per kilogram per degree Celsius. Assume potato enters at 24 degrees Celsius. The initial temperature of potato was at 24 degrees Celsius, which is also the ambient air temperature, and leaves at the same temperature as the exit air, which is 71 degrees Celsius. And you were asked to draw a system diagram of this process, and almost all of you have submitted except for several persons. Yes, all have been submitted. 64 has been submitted. So 64 has been submitted. Some have been graded already. Some of. So, for example, Zakro has submitted his diagram. Okay, very nice diagram. So you have potato going inside into the dryer. Coming in, the hot air is coming in at 80 degrees Celsius, coming out at 71 degrees Celsius. So the potato is at the temperature of 71 degrees Celsius with 10% moisture from initial moisture content of 80%. And the hot air is being heated actually by steam at 70 kilopascal, and so air has been heated in this heat exchanger from the room temperature 21 degrees Celsius and going out to the dryer at 80 degrees Celsius. So very nice diagram from Zakrul. Okay. 100 kilogram of raw material, which is the potato, is with 80% of moisture. That is 80 kilogram of water and 20 kilogram of dry material, such as starch. So total weight of the dry product is actually 20 times 10 out of 9, which is 22.2 kilogram. This is how you calculate the dry product. Yeah, and weight of water of the dry product, which is now 20. Which is now 10% moisture. So 22.2 minus 20, and then you have about 22.2 kilogram of water. Yeah. So amount of water that is being removed is 8T minus 22.2, which is 77.8 kilogram has been expelled out of the potato. Heat supplied to potato product, sensible heat. So what is the heat that will be supplied to the potato product so that water will be evaporated, which is the sensible heat to raise potato product temperature from 24 degrees Celsius to 71 degrees Celsius. So the air temperature will be the same as the potato temperature. Yeah, it is 24 degrees Celsius, not 21 degrees Celsius, up to 71 degrees Celsius, and plus the latent heat of vaporization. The amount of heat required is the heat to raise the temperature and also the heat required for vaporization. So the latent heat of vaporization corresponding to a saturation temperature of 71 degrees Celsius, saturation temperature of water, yeah, of steam at 71 degrees Celsius. And this is usually given, or you can find out from the table, is 2331 kilojoule per kilogram. If I ask the as a student for chemical engineering students, they have to find out this value from a table. Yeah, in their examination, there's a big, very thick book. We call it as a handbook that they have to find this value of latent heat of vaporization. They have to find themselves, but for you yourself, the lecturer must provide this value, yeah, in the question. Okay. Heat minimum supplied per 100 kilogram is 100 is 100 kilogram, and T 3.43. What is 3.43? Is the specific heat. Yeah, so this is mCp delta T. mCpm is 100 kilogram. 3.43 is the Cp of the potato, and the delta T is 71 minus 24 degrees Celsius, plus latent heat lambda, which is 2331 times m. M is the amount of water, mass of water. Weight of water is 77.8 kilogram. The amount of water that will be displaced or expelled is 77.8 kilogram times the lambda, or the latent heat of evaporation, 2331 at 71 degrees Celsius. So there you have 1.97 times 10 to the power of 5 kilojoule. Yeah, when you do this calculation, you will get the final number of 1.97 times 10 to the power of 5 kilojoule. Heat to evaporate water only is 77 times the lambda, or the latent heat of evaporation, 77.8. This is equals to 1.81 times 10 to the power of 5. Yeah, 10 to the power of 5 kilojoule. Not 105, yeah, 10 to the power of 5. Ten to the power of 5. I don't want to waste my time to do that. No, you must know that this is 10 to the power of 5. Yeah. The specific heat of air is given 1 joule per kilogram per degree Celsius, and the density of air is actually, so the density of air, which is rho, is 1.06 kilogram per meter cubic. Yeah, and this can be obtained from Appendix 3. Heat given up by the air per 100 kilogram of potato is Cp delta T. So Cp delta T, Cp of air 1 times 80 minus 71. This is the delta T, the temperature difference, times 49,800 times this is the lambda. This is the 49,800 is the amount of air, which is in the flow rate of air, which is 49,800 meter cubic. So you have to calculate with the density to get the kilogram. Yeah, you have the volume, 49,800 meter cubic, and this is the density. So this is to convert air into kilogram of air. Yeah, to convert from volume into mass. Yeah. So you have 4.75 times to the power of times 10 to the power of 5 kilojoule. This is heat given up by the air because of the cooling 80 to 71 degrees Celsius. The latent heat of steam at 70 kilopascal gauge, the temperature for the operation is 70 kilopascal gauge, which is gauge, and then you have to add up with 100 of atmospheric pressure. So you have absolute, ABS stands for absolute pressure, 170 pascal absolute pressure is given 2216 kilojoule per kilogram. Usually you have to find it from a table at 170 pascal absolute, 170 kilopascal, yeah, 170 kilopascal, this is wrong. Absolute, from the table you will obtain the latent heat of steam is 2216 kilojoule per kilogram. Thus the heat in steam is lambda times the amount of steam, which is 250 kilogram is given. Yeah, is given 250 kilogram. Where is it? 250 kilogram of steam is given. 250 kilogram times 2216, which is the latent heat of evaporation of steam. So you have 5.54 times 10 to the power of 5 kilojoule of latent heat of steam. Therefore, efficiency is equal. So you have to use the formula equation for the efficiency. Eta equals to T1 minus T2 divided by T1 minus TA. Yeah? So you have to use this formula. Efficiency based on latent heat of vaporization only. 1.81 is the heat to evaporate water only, and 5.54 is heat in steam, latent heat of steam. Yeah. 1.81 is the heat to evaporate water, and the heat supply by the steam is 5.54 times 10 to the power of 5 kilojoule. Heat that is required to evaporate water is 1.81 times 10 to the power of 5 kilojoule. Thus, the efficiency based on latent heat of vaporization only is this. Yeah, this is the amount of heat required and amount of heat provided by the steam, and amount of heat required. 1.81 is amount of heat required to evaporate the water, and this is 5.54 is the amount of heat supplied by the steam. So it's only 33%. Okay, 1.81 divided by 5.54, so you have only 33% of efficiency. B, efficiency assuming sensible heat remaining in food after drying is unavailable. If you don't have the sensible heat remaining in food after drying, you should know it. You can calculate, but it's not there. so it's not available. So 1.97 is the heat supplied to the potato, yeah, based on potato. So this is based on the heat remaining in food in the potato, 1.97, and then 5.54 is the one that is supplied by the steam. Okay, so based on heat remaining in food, so you have a higher efficiency of 36%. Efficiency based on heat input and heat output, yeah, in drying the air. So eta base eta, which is efficiency, equals to T1 minus T2 divided by T1 minus TA. A is the air, yeah. So T1 80 minus 71, T2 is the outlet temperature, T1 is the inlet temperature of air, and T2 is the outlet temperature of air. T1, of course, 80, and T of air is 24, so eta is equals to 16%. Okay, this is how you calculate the efficiency, but with different numbers, yeah, based on what are you referring to. Yeah, this one is efficiency based on the latent heat of vaporization. This B, efficiency assuming sensible heat remaining in food after drying is unavailable, and efficiency only based on the temperature of the dryer. Okay. Mass transfer in drying. Mass transfer means how much water is being transferred out from the food. Yeah. In heat transfer, heat energy is transferred under the driving force provided by the temperature difference. Yeah, the higher the temperature, so you have better drying. The rate of heat transfer is proportional to the potential temperature difference and to the properties of the transfer system characterized by the heat transfer coefficient. Thus, in the same way, mass is transferred under the driving force provided by a partial pressure or concentration difference. Yeah, so a partial pressure between the moisture, the pressure of water in the food, and the pressure of water in the air, in the drying air. The rate of mass transfer is proportional to the potential, that is pressure or concentration difference, and to the properties of the transfer system characterized by mass transfer coefficient. Yeah, I'm not going to go into deep on this mass transfer coefficient because it is not required for you in your syllabus. So we just want to introduce to you, there is a mathematical equation that explaining about the mass transfer phenomena in drying. So writing this symbolically, analogous to Q equals to UA delta T, so with the same pattern of equation like the heat transfer, so Q equals to UA delta T. Thus, you have dW over dt equals to kg prime A delta Y. So what is dW? dW is the mass of moisture or water being transferred in kilogram per second in time. dt is time, usually in seconds. A is the area through which the transfer is taking place, and kg prime is the coefficient. We call it as the mass transfer coefficient, and the unit is kilogram per meter squared per second. And delta Y is the humidity difference in kilogram per kilogram. The humidity difference between air and in the food. Usually air is the is the material or the medium for heating, and it is also a major heat transfer medium. Therefore, it is necessary to look carefully into the relationships between air and the moisture it contains. So there is a relationship in the form of equation or in the form of table. Yeah, the data is tabulated, or you can use an equation to relate between air and the moisture, the amount of moisture. So we can use this psychrometry. Yeah. So the capacity, it is defined as the capacity of air for moisture removal depends on its humidity and its temperature. Amount of moisture that can be carried in air depends on its humidity of the air and the temperature as well. So the study of relationships between air and its associated water amount is called psychrometry. Humidity, usually with the symbol Y, is the measure of the water content of the air. The absolute humidity is the mass of water vapor per unit mass of dry air, and the units are therefore kilogram per kilogram. Absolute humidity is often called just humidity, and in this text, in many of the textbooks as well, it is named absolute humidity or humidity ratios in charts. So air is said to be saturated with water vapor at given temperature and pressure if its humidity is a maximum under this condition. So at certain temperature, the amount of maximum air that can be contained by the air, amount of water that be contained by the air is called as a saturated vapor. If further water is added to saturated air, it must appear as liquid water. So you will have a droplet of water where you can observe in our atmosphere when rain occurs. Yeah, the phenomena of rain happens when the level or amount of water in the air is exceeding the saturated water vapor. So it must appear as liquid water in the form of a mist or droplets. So there you will observe the raining phenomena. Under condition of saturation, the partial pressure of the water vapor in the air is equal to the saturation vapor pressure of water at that temperature. The total pressure of gaseous mixtures such as air and water vapor, so air also contains different gases such as nitrogen, oxygen, and CO2, is made up of from the sum of the pressures of its constituents, which are called the partial pressures. Yeah, so air, a mixture of air and water vapor, so you have different value of pressure for air and water vapor, and we call this as a partial pressure. Partial pressure for water, partial pressure for air. Each partial pressure arises from the molecular concentration of the constituent and the pressure exerted by each gas, that which corresponds to the number of moles present and the total volume of the system. So if you have a system which contains air plus water vapor, so the total pressure and as well as the partial pressure depends on the concentration of the species, yeah, or the constituent inside the mixture. The partial pressures are added to obtain the total pressure. Okay, these are factual that you need to understand. And wet bulb temperatures. What it means by the wet bulb temperature? It is the temperature reached by a water surface, such as that registered by a thermometer bulb surrounded by a wet wick when exposed to air passing over it. So when you have a bulb of temperature thermometer, yeah, and then you rendam dalam air, then you have a wet wick of water, then that temperature we call it as a wet bulb temperatures. Okay, this is the a chart, we call it as a psychrometric chart, which contains 3 parameters. What are the parameters? Enthalpy, temperature, the dry bulb temperature, and you have the absolute humidity. Okay, enthalpy, dry bulb temperature, and then absolute humidity. Dry bulb temperature means that thermometer is not covered with moisture or water. Yeah, so you have enthalpy, the unit is kilojoule per kilogram. You have absolute humidity, kilogram per kilogram, and of course the temperature in degree Celsius. Yeah, there you have the saturation line. You have a constant relative humidity, constant volume, wet bulb lines of 20%, and then with different percentage of humidity, 60%, 40%, 20%, 10 degrees Celsius. So these are the temperature line, and these are the relative humidity line. What you need to understand is that psychrometric charts contains 3 parameters: enthalpy, dry bulb temperature, and also absolute humidity. Air drying. In air drying, the rate of removal of water depends on the conditions of the air, the properties of the food, and the design of the dryer. Water in a food came into one or other of the 2 categories, free water or bound water. What it means by free water, what it means by bound water in food. So water is held by forces whose intensity, the value of the forces, ranges from the very weak forces retaining surface moisture to very strong chemical bond. So you have chemical bonded water. Water that is loosely held will be removed most easily. So drying rates would decrease as moisture content decreases. The rate of drying will be decreased when you have decreasing in the moisture content, with the remaining water being bound more and more strongly as its quantity decreases. So the bound water is harder for it to be removed. Part of water is loosely bound. This water can, for drying purposes, be considered as free water at the surface. Yeah, this is the typical diagram for drying rate curves. Yeah, some of you have done experiments for final year project on the drying kinetics. Yeah, so drying kinetics meaning that what is happening over the time. You have drying time here in minutes, 20, 40, 60, 80, 100, 120 minutes, and you have the drying rates. The drying rate kilogram per kilogram per hour, kilogram per kilogram per hour, kilogram per kilogram of food, kilogram of water per kilogram of food per time unit, which is per hour. Yeah, so the normal pattern of the drying kinetic curve is that you have increment, you have constant rate drying, and then you have decreasing in rate drying. Yeah, so you have increasing constant rate drying, and then you have this bound water, yeah, hard water to be removed. Then you have reducing rate of drying. This is a typical curve for minced meat. Okay, so some of my students in doing FYP just do the drying curve for different type of material, different type of food material. Okay, that's all for my lecture. Now it is for your assignment, or rather, yeah, assignment. I would like you to repeat this assignment to calculate the efficiency of a potato dryer. What you have to do is to repeat the calculation. You have to understand all this calculation. Yeah, this calculation did not come with the symbol of the parameter. So you have to find out what are these 22.2 minus 20, all this thing, lambda, m, how to calculate the m. So what you going to do is to repeat this calculation for finding the efficiency of a potato dryer. And now I'm going to change on the mass of potato, yeah, the weight of the potato, and the rest is the same. Okay, just change the amount of potato, and then you are going to repeat the calculation. You will calculate 3 types of efficiency. Yeah, efficiency based on latent heat, efficiency based on sensible heat, and efficiency based on the temperature, okay, of the drying air. So I'm going to change the amount of potato to 200 kilo, 1.5. We cannot do as a simple number, quite a different number. So 156 kilogram of potato. Yeah. So I'm going to copy this instruction or question, and then I'm going to post it in the e-learning. Yeah. So you are supposed to read the instruction in the e-learning for this new assignment. Yeah. And then you're going to do it, or I think you can finish up in 1 hour time, and then you can write it on a piece of paper, and then take a snap of photo and then submit into the e-learning, the landing page. Okay, I hope you can understand this. Any problem, then you can post your question in the WhatsApp group. All right, I suppose that's all for today. Thank you very much indeed.